let's make a start. So I guess if you don't remember anything from the last lecture, or everything was confused. So, but at least hopefully one thing you can take home from the last hour of discussion is this fundamental commutation relation, which basically is quite easy to motivate. You should really view this relation as, for example, today they can be, so each of those so external vertex here are really like an incoming particle or some quantum laboring by some quantum mechanical states, and it carries, for example, for the auxiliary kind of physical auxiliary space, that they will be laboring by some external, some complex parameter lambda and mu. But the key point here is that only the exchange between the kind of auxiliary space and physical space, which labeled by n, are actually kind of physical. Therefore, the exchange or the scattering between the auxiliary space themselves, or basically V1 and V2, it should not matter that whether such exchange actually take place before, this will be like a before, so time will go this way, before or after the scattering between the kind of the auxiliary particle and the physical particle. So this is what this diagram actually means. So we can actually, for example, bring this line. So this will be the one after the exchange of auxiliary space, but we can actually bring forward in time to this way. So we can have a kind of physical scattering process take place first, and then you have this exchange or the scattering in the auxiliary space. And those two, your final result should be exactly equal to each other. So that's what this fundamental commutation relation actually means. So just write down again what the line or what the R matrix actually is. But if you really want to kind of prove it via the, so hopefully like you can try to prove this commutation relation in this rather kind of abstract way, or basically this graphical way. Sorry, this graphical way. But if you want to prove it just straight from multiplying the matrices, then you can prove it by, remember, you can prove it by using, for example, the obvious property of a permutation operator. And of course, if you change the two space one way, should be equal to the exchange operator, permutation operator. So it is this one. So you can actually use this to show and use the definition of the R matrix to show this fundamental commutation relation. Okay. So actually the next operators Ln A we can write it as some kind of 2x2 matrices acting on the auxiliary space, but now, so I'm basically writing out in the components acting on the auxiliary space, but with entries being the operators on the physical space. So all these are kind of 2 by 2 matrices on the Hilbert space Hn. And in the literature, that there is this interpretation that the Lax pair, the Lax operator, actually it's more obvious. I would refrain from using in the notes. I say this as Lax operator. Oh, okay, I said it take you from psi n plus 1 to psi n and so on. But here, right now, it's actually not so obvious. But I would rather postpone this interpretation when we come back and actually see how the momentum, or lattice momentum operator, actually appear from this formulation. But right now, I'm just going to write it like this. And then hopefully you will bear with me. I guess you have been bearing with me. That a little bit. Let me introduce another quantity, which is a transfer matrix. But it's really nothing but an order product of all the lattice matrices together. So I will drop this bell, keep log line. So I would define another quantity. Well, I guess that would be something natural you would be doing, even if you didn't know any physical interpretation, would be that, well, so now if we introduce a Lax operator for a one lattice size, why don't we, and we know how they then if you, and we know how they kind of multiply each other or their commutation relation, then why don't we think about what happens if we multiply all these Lax matrices together along basically for all the individual lattice size, and indeed, so we can define something called a transfer matrix, which is something like T and A lambda. And that's an order product of N A lambda and minus 1 A lambda dot 1 A lambda. So basically this guy now acts on basically talk about auxiliary space V, and then H1 and the product Hn. Okay. So we can again write it as some kind of 2 by 2 representation, but of course you should into something like this. So this will be a 2 by 2 matrix on the auxiliary space, but individual entries here, you should really remember that they are kind of operators on the remaining kind of physical space on your spin chain, just like what we have here. So they are really kind of products of the of those Pauli matrices which acts on the individual spin chains. Okay, so what does this buy us? First, if we define it the transfer matrix into this way, we can actually use the fundamental relation. So I will actually drop the index capital N here, because I assume like all the lattice side has n spin for now. So I'm just going to denote it as TA lambda. So we can actually, from this guy, to deduce a similar commutation relation between the transfer matrix, and the form should not come as a total surprise to you, because once you realize, well, okay, unfortunately I wiped the diagram, but yeah, this is obvious, because you can even guess what I'm going to write down, because now, again, I will consider, say, another auxiliary space, V1 and V2, and then I can define another transfer matrix associated with, one will be lambda, and one will be mu. And if you knew what was happening just now, then you can almost write down the transfer matrix. So the commutation relation for the transfer matrix in this case graphical proof of this relation. How many of you this diagram is obvious? Or as a proof to this guy? You can raise your hand. It's that obvious to you. You don't even have to. You are convinced this works. Great. So you actually know what's going on. Yeah. Because indeed, again, we are looking at the scattering. So all this physical scattering process between the if you want the individual lattice side with the auxiliary space. And of course, as a final process, it should not matter that kind of exchange in the auxiliary space given by this matrix R12 happens before all the physical scattering or after the physical scattering. And that's what this guy actually tells you. And if you want to wipe out all the lines in the middle, then you get back to what we have over here. So, and this fires something very nice. So, let me make some comments. Actually, this kind of Young-Baxter equation you will also see in the context of conformal field theory that they appear as a kind of fusion relation between different correlation functions in various other places. So if you are interested in going into theoretical physics, then I guess you will encounter this kind of relation quite often in your career. So so of course you can prove this relation by the fundamental commutative relation and so on. So, okay, so a few comments. So the transfer matrix TA lambda is actually a polynomial, and this is actually a key. lambda of a order or degree n. So if you actually expand it out in lambda, you actually see this guy actually looking something like lambda to the n plus I lambda n minus 1 alpha 1 3 s alpha and all the lower order terms. So that's basically saying that there are no poles because it's a polynomial operator. If you act on later on, this is an operator acting on some Hilbert space. But the key point is that because it's polynomial, its eigenvalue does not have any poles. And this is actually crucial later if you want to derive the famous Besser-Ansatz equation. So, like what we usually do with matrices, the next thing, what can we do? So now it's operators on the auxiliary space A. Then we can think about if we trace over. Let me just write down this guy again. So I denote something like A lambda dn lambda cn lambda dn lambda. Okay, so we define another quantity which is actually going to be a generating function for all the conserved charges in our system. Which is simply given by the trace of the transfer matrix over the auxiliary space itself, and that's of course equal to an lambda plus dn lambda. So we kind of trace over the auxiliary space, and now you only have three indices which will act on the physical Hilbert space. And the punchline we will show now is that this operator is actually kind of the kind of operators will encode all the physical conserved charges in your system. And in fact, those conserved charges are all commuting. And this is again, so I will write it again just because just like the transfer matrix can be written as a polynomial of integral lambda. The f lambda is also a polynomial in lambda. But now, because of trace, we are tracing over the Pauli matrices. So that means the trace of Pauli matrix is actually 0, and that means the coefficient for lambda n minus 1 actually vanishes. So that's why you have summation only go up to n over 2, or minus 2, sorry. But otherwise, you have something like this. And all this expansion coefficient, the q lambda here, is actually, well, I should really have a q l hat. They are actually kind of operators, or quantum mechanical operator, for the conserved charges. And in fact, momentum also sits in there, or momentum will be function of those, and position, sorry, and the Hamiltonian will be function of those QL, also conserved charges, as we will show now. And this is actually exceedingly easy to show, because now we are given this relation. All right. So let me write this obvious proof down. So first thing we can do is that we take I will call this, give this another name as a fundamental commutation relation 2, NCR2. Well, so if you multiply left and well, basically both sides by R A1, A2 inverse, say from this way. So we cancel this guy, we give you another one here. So we'll have something like TA1 lambda TA2 mu is equal to R A1 A2 minus 1 lambda minus mu. And you have TA1 lambda TA2 of TA2 mu TA1 lambda times R A1 A2 lambda mu. Okay. But now if you trace over both A1 and A2, okay, and if you use a cyclistic properties of the trace, then basically this guy cancels with this guy in a trace. You can use a cyclicity to prove that. So what do we have? Well, so I will keep about this one. So we simply get the following, which is what we call F lambda F mu equal to 0. So you can imagine this is like a trace of A1, T, A1 lambda, and this is like a trace A2, A2 mu. Which are those generating functions? Yeah. So each of those F lambda and F mu are just some polynomial in lambda and mu respectively for kind of arbitrary lambda and mu's. So therefore, for the commutation relation to actually work, that implies that all the coefficients, expansion coefficients for F lambda and F mu, which are basically quantum mechanical operators, Q. Well, so you can have one of those, and then you can have this guy, something like 2 mu n plus k equal to 0, n minus 1, q half k mu to the minus 2, sorry, mu k. That means all these guys commute with each other. So basically, what do we have? Now we have n minus 1. So this is run from 0 to n minus 2. So therefore, yeah, n minus 1 coefficients. Well, I choose a normalization to be, I take this to be a factor to be 2. Well, of course, you can do it the other way to normalize your constants. But anyway, so we get n minus 1 commuting operators. So to be most precise, to say they are also conserved, we need to show that the Hamiltonian, just like in the classical mechanics, that you want to show each of those Q's are actually commuting with the Hamiltonian itself. But a good way to show this would be simply that to demonstrate the Hamiltonian is actually functions of those individual commuting operators. And therefore, if they commute with each other, the Hamiltonian, of course, also commute with those operators. So we have n minus 1 commuting operators. And of course, some of you may recall that just now, because we are doing the trace, we threw away the spins, which of course is also a commuting operator in your system. So that gives you another one. So add up to this n-1 commuting operators. Altogether, you have n commuting. In fact, later I'll show momentarily that conserved operators. So that's actually what you need for the integrability in this case of string channel n size. So to show, and actually this will also make it more clear the roles of all this lax operator, because they are actually like the kind of momentum operator or transfer. Or basically take you from one lattice side to another lattice side. So let me just do that. So to show conservation, we want to show Hamiltonian is actually inside all these conserved charges and operators. Well, so what we can do is we can first consider the momentum, or basically the following. Actually, let's consider. I was showing just now that the lax operator depends on a special parameter. But now, if we consider the parameter equal to a special value of I/2, this is actually kind of proportional to the permutation operator between the physical space N and the auxiliary space BA. And also another little useful identity is that okay. So that's saying what we call a transform matrix. But if we now set the special parameter to be I/2 also, then we basically get something like this. A, B, and -1, A, okay. So all these are kind of permutation operator between the each individual lattice side and the auxiliary space. But magical things happens if we take now trace over A. Because now, let's say, if we're using the properties of the permutation operator, you should really try to convince yourself this is the case. Now, just simply acting on the vector space and the Vn, the Hn, Hn, and V. This really is what it does. And finally, the trace A, P, A, N equal to that kind of identity matrix over N. We can show that now if you trace over A here and do the permutation, so we can show that, so trace A, P, A, I/2, which is what we call F, I/2,